So how we define entropy? Entropy simply refers to the disorder in the system is refers to entropy. And entropy of a process, natural process, with either will be constant or it increases. So example, you have say 4 particles. In terms of chemistry, how we can define this entropy? It's the possible ways by which energy distribute among the particle. That's also called entropy. So started with like example, you have 2 particles and the total energy of the particle is 10 joules. The sum of energy of the 2 particles, that's equal to 10 joule. So what are the possibilities how the energy can be distributed between the 2 particles? So there are different possible ways. Maybe all of the energies having particle 1 is having all the 10 joule and particle 2 is having 0 joule. Maybe particle 1 is having 9 joule and particle 2 is having 1 joule. The sum should be 10. Maybe particle 1 will have 8 joules and particle 2 will have 2 joules. And so on. A particle 1 may have 7 joules and particle 2 may have 3 joules. So this is a disorder in the system because there are many possibilities that the energy can be distributed between the 2 particles in this example. So multiple ways by which energy can be distributed, what we call or what we call that as entropy of the system. So disorder in the system is simply known as entropy of the system. And entropy of a system increases if we have more energy or if we have greater number of particles. Because if high energy is there, there are more ways by which energy can be distributed between the particles. Or if greater number of the particles, again, there are many possibilities by which the energy distributed among the particles. Then using an entropy, how we can find whether a reaction is spontaneous or non-spontaneous. So the term spontaneous reaction means if a reaction proceed by itself without any external influence, we call that as a spontaneous process. But if a reaction does not proceed or does not form a product, if a reactants are not able to form a product, then we call them as non-spontaneous reaction. Normally, if a reaction is exothermic reactions are spontaneous reactions. Why we call exothermic reactions are spontaneous reaction? Because the reactant can take energy from the surrounding, very small amount of energy, they can take energy from the surrounding. They reach the activation energy, the minimum possible energy for which the reaction start, and then they will form the product. Like example, burning of a petrol or even burning of a matchstick. So what you have to do, if you want to burn a petrol, if you want to ignite a petrol, a small thing what you have to do, you need a small spark. So what this spark will do, this spark will provide energy for the reactant so that they will reach activation energy. Once the reactant reach the activation energy, they will form a product. Because the product is having low energy, that's why most of the energy is released. So as greater amount of energy is released, what happened? The energy which is released, this will help the other reaction to proceed. And that's why we call this as a spontaneous reaction. So spontaneous reaction without the influence of the external condition, a reaction can be carried out. Same way, for a spontaneous reaction, we also define a term, kinetic stability. There are two types of stabilities. One is known as kinetic stability, another one is thermodynamic stability. Stability of the reactants can be termed as kinetic or thermodynamic. The term kinetic stability means the reactants can form product, but the conditions does not favor the reaction, or a small difference in energy between reactants and activation energy. So when there's a small difference between the energy of the reactant and activation energy, or reactants have potential to form a product, but still they're not forming a product. So we call these type of reactants, we call them kinetically stable reactants. Example of kinetic stable reactant, like example, you're using a petrol or a gasoline inside the car. So you have, for this reaction, what is the equation? Gasoline or petrol, it's octane. Octane means C8 and H18. When you burn in the presence of oxygen, this should give carbon dioxide and water vapors. But what happened, even though in a fuel tank or even in the engine, you have gasoline or you have petrol and you have oxygen, but oxygen and petrol will not react with each other until unless you change a slight change in condition. The reactants can form a product, but still they are not forming a product. So if they're not forming a product, we call this mixture of the reactant as kinetic stable, or they have kinetic stabilities. So most of the exothermic reactions, the reactants are kinetically stable, means they have potential to form a product. Very small amount of energy is needed to start up the reaction so that it can form a product. So when we sketch a graph or energy profile diagram for reactant and product, so in exothermic reactions, reactant have high energy and the product is having low energy. A small difference between reactant and minimum possible energy to start up the reaction, and then it will form a product. So this mixture is kinetically stable. But what is thermodynamically stable? So thermodynamically stable mixture or a reactant means that there is a greater difference between energy of reactant and activation energy. When there's a greater difference between energy of a reactant and activation energy, this kind of reaction mixture or reactants are known as thermodynamically stable reactants. And most of the endothermic reactions, the reactants are thermodynamically stable. So when we sketch a graph, energy of the reactant is small, then they will form a product. They need a greater amount of activation energy, and then a product is formed. So energy of a product is higher as compared to energy of reactant. You have to supply energy so that you can carry out a reaction. That's why we call them as the reactants are thermodynamically stable. So for endothermic reaction, the reaction mixture is thermodynamically stable. For exothermic reaction, reactants are kinetically stable. Kinetically stable means the reactant can form a product, but the conditions are not suitable, or a small change in condition can form a product. Activation energy, the small difference or gap between the energy of reactant and activation energy, or minimum possible energy to start up a reaction. Is this clear? The stability of the reactant. So reactant can be kinetically stable or it can be thermodynamically stable. Is this clear? Yes, in the thermodynamically stable, the condition, like example, you need a high temperature. Normal example of thermodynamically stable, like thermal decomposition of calcium carbonate. So this gives calcium oxide plus carbon dioxide. In kinetically stable, conditions are there, but it's not. Okay, okay. You at this point, actually, I mean to say conditions favor. This is the reactant can form a product, and condition favor the reaction, but still the reactants are not forming a product. We call that as kinetic stability. So spontaneous process, the process which can proceed on its own without any external influence, we call that as spontaneous process. The delta H, the enthalpy change, if the reaction is exothermic, the delta H will be negative. If reaction is endothermic, delta H will be positive. And what does it mean here? The reaction that is exothermic will result in the product. The product is more thermodynamically stable than that of reactant, and this is a driving force behind many reaction and causing to be spontaneous. So most of the exothermic reactions are spontaneous. The reactants are kinetically stable and the product is thermodynamically stable. So entropy, when we consider the entropy, entropy means the disorder in the system. That's simply known as entropy. There are two things. One is entropy of a system, another one is entropy of surrounding, and the second thing is a total entropy. So total entropy is entropy of the system plus entropy of surrounding. And you will learn the formula to calculate the entropy of system as well as entropy of surrounding. So example, when you compare the entropy of the system, So when we are comparing the entropy of a system, entropy of element is less than compared to tend to have lower entropy than compound. Entropy of simple compound is lower than complex compound. Entropy of a pure substance is lower than entropy of the mixture. And if we sketch a graph for entropy and the change in state, so the disorder in the system is refers to entropy. Like example, you have a solid. In solid, the particles are having a regular arrangement, tightly packed together. You supply heat energy. When you supply heat energy, more energy is there. It means the particles, they have greater probability or distribution of energy. So what happened when you're increasing a temperature, the entropy is also increasing. So this part, when you have a solid, increasing temperature, increase entropy. Once a solid is melting, so when there's a state changes, there's no change in temperature. So what happens if temperature does not change? The value of the x-axis will not change, but the value of the y-axis will change. So particles move away from each other. Average kinetic energy of the particle is same, but they are moving away from each other, which increase the randomization of the particle. You can see there's an increase in entropy when the solid is melting. Once all of the solid is converted into liquid, further you supply energy. Increasing a temperature means increasing the energy, and increasing energy means increasing the entropy. But once all of the liquid reaches its boiling point, that there will be a greater change in state, and in gases the particles are moving faster and more random movement is there. That's why you can see when a substance, the state was changing from liquid to gas, there's a greater change in entropy as compared to solid was changing into liquid. When solid was changing into liquid, there's a small change in entropy. Reason for that, because still it will have a definite volume. But once a solid liquid is changing into gas, there's no definite volume. The particles are free to move, so they are having greater random motion as compared to in this liquid state. That's why the higher or a greater change in entropy. So when a boiling occurs, there's a greater change in entropy as compared to when melting will take place. And once you have gas, you supply energy to a gas, so particle will further move, so entropy will increase. So why here the temperature was constant? Because there's a change in state. And why drastic change or greater change from liquid to gas? Because more random motion as compared to solid to liquid. Is this clear? The graph between temperature and entropy. And when the temperature is 0 Kelvin, the molecule will stop vibration, or they don't have a kinetic energy according to theory. This is a theoretical. So they are not vibrating. There's no disorder in the particle. So that's why there is zero entropy. So solids have lower entropy than liquids, and which are lower than that of gases. And when a solid increases its temperature, the entropy increases. And there's a bigger jump of entropy when there's a boiling as compared to that in a melting, because the gases have larger entropy as compared to gases, because as compared to liquids, because gases have greater disorder in the system. Is it clear? The entropy of the system, entropy or disorder in the system. Then how we can, there are two ways. One is qualitative analysis. Another one is quantitative. In qualitative, you don't have to do calculation, just you will identify from the states that whether the entropy will increase or entropy of a system will decrease. So an increase in disorder means entropy will be positive. If decrease in disorder, entropy will be negative. And for this, you need a balance equation to just identify the entropy, what happened. Like example, ammonium chloride is solid, but when it decomposes into hydrogen chloride gas and ammonia gas. So there is hydrogen chloride gas and there is ammonia gas. So what happened? You can see the reactant is the solid, but the product is a gas. So if reactant is solid and the product is a gas, so what happened to entropy? Entropy will be positive, or entropy will increase because the solid is changing into gaseous, and you can see there's increase in number of molecules. So entropy increase as the number of the molecule increase. Entropy also increases as the state changes. When state changes from solid to gas or liquid to gas. You have another example, you have sodium solid, you have chlorine gas, it is forming sodium chloride. So gas turned into solid. So if a gas turning into solid, you have more particles, like 1.5 particles in the reactant side and only one particle in the product. So number of particle decreases, as well as the solid is having lower entropy as compared to gas. So according, the qualitative analysis shows that the entropy of the system should be negative. Is this clear? This is qualitative analysis. Like we don't measure anything, we just identify by number of the particles or states. But then there is also quantitative analysis, like there is the way to calculate the entropy of a system. So what is the formula to calculate the entropy of the system? The formula to calculate the entropy of a system is entropy of a product, standard entropies, or entropy of a product minus entropy of the reactant. Summation means sum of entropy of and that will be given, and the unit of entropy is joule, Kelvin inverse, mole inverse. So it is basically energy divided by temperature and divided by mole. That's a unit of energy is joule, temperature is Kelvin, and mole unit is mole. So how we can calculate the entropy of the system for this? Iron oxide react with carbon, it gives iron plus carbon dioxide. If we check, we have solid, like 5 particles are there, and 4 plus 3 7 particles. So number of particle increase, as well as the state. First reactants are in a solid state, but the product, one of the product is in gaseous state, so the entropy should increase. Now how to calculate this entropy? That's a qualitative analysis, but quantitative analysis means how we can measure this entropy change. So entropy change is a product minus reactant. The sum of entropy of a product minus sum of entropy of reactant. So product is what? It's iron plus carbon dioxide. Standard entropies or entropies are given. For iron, it is given 27.3. For carbon dioxide, it is given 213.6. So because we have 4 moles of iron, that's why for iron it is multiplied by 4. And we have 3 moles of carbon dioxide, that's why it's multiplied by 3. Because for every mole of carbon dioxide, the entropy change is 213. But in this example, there are 3 moles, so that's why it is multiplied by 3. So the formula is the entropy of a product minus entropy of a reactant. So product, Product we calculate for product, and for reactant how we calculate the entropy for carbon is there, which is 5.7 multiplied by 3, and for iron oxide 2 moles are there. For each mole it is 87.4. That's why it's multiplied by 2. When you solve, you will get positive 558 kilojoule per mole. Actually it's joule per mole Kelvin, or joule Kelvin inverse mole inverse. You should always write your answer in 3 significant figures. So this is how we calculate the quantitative analysis of entropy of the system. Is this clear? So always the product minus the reactant. Then entropy of a surrounding. What is how to calculate entropy of a surrounding? Basically, what happens if the reaction is exothermic? Exothermic reaction means it release energy. Release energy where? It release energy to the surrounding. So if energy is given out, so with the particles which are there in the surrounding. So as we know, entropy increases as the number of the particle increase, or if they have a random motion, or they have more energy. So as you can see, if a reaction is exothermic, the exothermic reaction give out energy. As the exothermic reaction give out energy, what happened to the particles? Entropy of the particles of surrounding, according to qualitative analysis, it shows that entropy will increase or entropy will be positive if the exothermic. And if it's an endothermic reactions absorb energy or take in energy. So if it absorb energy or take in energy, so what happened to the entropy of the surrounding? The entropy of a surrounding will decrease, and when entropy decrease, we say it's a negative value. This is in qualitative analysis, like in terms like a theory. But how we can calculate practically? So practically it is calculated by a formula. Entropy of a surrounding is minus delta H by T. And you can see here, as it is minus delta H by T, for exothermic reaction, delta H is negative. So if I say entropy, this sign is for standard. If you remember AS, standard condition, if it is done at standard condition that you have 1 mole of a substance at 1 atm, 298 Kelvin or 25 degrees centigrade, and pure form of a substance is used. So then we say these are the standard conditions. So standard entropy of a surrounding is equals to minus delta H by T. And as we know, this delta H will be negative for exothermic reactions. So as this delta H will be negative, minus will multiplied with minus. So final answer will be positive. And if the reaction is endothermic, the delta H, the change in enthalpy, is equals to positive. So when you substitute a positive answer here, the final answer for entropy change will be negative. So for exothermic reactions, entropy of a surrounding increases, and for endothermic reaction, entropy of a surrounding decreases. And if we need a total entropy, the formula to calculate the total entropy is the entropy of a system plus entropy of surrounding. If the total entropy is positive, it means the reaction is spontaneous. The reaction will proceed or reaction will occur. If total entropy is negative, it means the reaction will not form, the reactant will not form a product, or reaction is non-spontaneous. Is this clear? The concept of entropy of the system as well as total entropy change. Now, this is an example in which you have to calculate the total entropy So this is an example in which you have to calculate the data for the following reaction, which represent the reduction of aluminum oxide by a carbon. So according to the what is the qualitative analysis shows, you have solid, solid, solid and gas. So qualitative analysis, according to the number of the particle, like 4 particles in the reactant side, 5 particles in the product, and you have more solid, like reactants are in a solid, but one of the product is a gas. The product involves solid and a gas. So it shows that according to qualitative analysis, it shows that the total entropy of a system should be positive. But it is not necessary that total entropy of a system. You have to work out the qualitative analysis. Sometime it is true, sometime it is not accordingly to the practical values. So how to calculate the total entropy? First thing, if you want to calculate entropy of a system, it is a product minus reactant. So what is a product? We have aluminum as a product and we have carbon monoxide also as a product. So entropy for aluminum is given and for carbon monoxide. 2 moles of aluminum, that's why it is multiplied by 2. And 3 moles of carbon monoxide, that's why it is multiplied by 3. That will give us entropy of a product. What about entropy of a reactant? So 3 moles of carbon and 1 mole of aluminum oxide. So 3 moles of carbon and 1 mole of aluminum oxide you will substitute. And when you solve, you will get entropy of the system as 581 joule Kelvin inverse mole inverse. When you calculate, because to calculate entropy of the surrounding, we need enthalpy change, delta H. And how to calculate enthalpy change? Enthalpy change is the enthalpy of reactant, enthalpy of a product. Because how you will calculate or get the enthalpy change for this reaction, the formations are given. So you have to recall the idea to calculate the enthalpy change. If you remember in AS, if you want to calculate the delta H or enthalpy change for this reaction. So delta H. So we have reactant, we have product, but we will add another link. And what is that link? We'll add carbon, the element. We'll add aluminum, and we will add oxygen. 3, so means it will be 1.5 or 3 by 2 O2. So maybe this will form a product or this will directly form a product. The Hess law. So if reactant form a product, if an element form a reactant or element directly form a product, according to Hess law, the overall energy change is independent of the path or the route which we follow. So this is where the 2 arrows are pointing out. That's the start of the cycle. Where 2 arrows are pointing in, that's end of the cycle. So if I follow route 1, the overall energy change is same as route 2. When element form the compound, that's called a formation. So this is a formation of aluminum oxide. And 1 mole of aluminum oxide is formed, so it's formation of aluminum oxide. It's not a formation of carbon. Why? Because the carbon was before and after, it was same. Same thing, this is the element forming a compound. So this is a formation of carbon monoxide. And according to Hess law, the overall energy change is independent of the route. So formation of aluminum plus enthalpy change or delta H for this reaction. So enthalpy change of formation of aluminum oxide plus delta H, the enthalpy change of a reaction is same as enthalpy change of formation of carbon monoxide. So we need delta H. So how to get it, find delta H? So delta H is enthalpy change of formation of carbon monoxide. That's given minus the enthalpy change of aluminum oxide, which is minus 1169. Is it clear? how to calculate the enthalpy change of the reaction. Because first, to calculate the enthalpy of a surrounding, we should know the enthalpy change of the reaction. Formations are given, so that's why we add another link, that is element. So after getting the enthalpy change of this reaction, which is 1136, so calculate the enthalpy change of a surrounding minus delta H by T. So we have the delta H, we substituted the value, and temperature should always be in Kelvin, so 298. So we divide, we get the enthalpy change of surrounding. And total entropy is a system plus surrounding. So system was 581 and the surrounding was 4,483. When you solve, you will get a negative answer. So whenever you get a negative answer, what it shows that this reaction is non-spontaneous, or it is not feasible, or you can say reactants are thermodynamically stable. Is this clear? This example, you'll find these type of questions. These are the exam style questions. Step by step, you have to do these questions. In exam, it will be stepwise rather than in one question they ask the final answer. Like first they will ask enthalpy of the system, then they will ask enthalpy change of a reaction, then they will ask entropy of surrounding, and at the last total entropy. And using a total entropy, whether a reaction is spontaneous or non-spontaneous. Is it clear?